Now that we know the meaning of a binomial random variable, let's determine how to calculate its probability. In the 2018 to 2009 NBA season, Kevin Durant made 41.6% of his three-point shots. If Kevin Durant took 5 three-point shots in a game, find the probability that he made exactly 2 of them. Well, this problem definitely contains a binomial random variable. There is a set number of shot attempts or trials being made, and that's 5. And in each shot attempt, Kevin Durant either makes the shot or misses it. In other words, there's a success or failure going on each time. The shots are independent of each other, meaning one shot does not impact the others. And the probability of him making the shot is that consistent 41.6%. If Kevin Durant makes 41.6% of his three-point shots, then he misses 58.4% of his three-point shots. And these values can be written as probability of success equals 41.6% or 416 thousandths, and the probability of failure is 58.4%, which is 584 thousandths. To figure out the probability that he makes exactly 2 of the 5 three-point shots, we need to determine the different ways that Kevin Durant could make the 2 three-point shots in 5 attempts, and calculate the probability of each of these different ways. So let's determine the different ways that Kevin Durant could make 2 three-point shots in his 5 attempts. For example, he could make his first 2 three-point shots and miss the rest of them. This would map out as success, success, failure, failure, failure. Well, what's the probability that this event will happen? Well, it'll be 0.416 times 0.416 times 0.584 times 0.584 times 0.584, or 0.416 squared times 0.584 cubed. Well, is this the only way that Kevin Durant could make 2 three-point shots in 5 attempts? Take a moment to think about it, and when you're done, unpause the video. Well, of course not. There are other ways in which he could make 2 free throws and miss 3 of them. He could do failure, success, failure, success, failure. What's the probability that this is going to happen? Well, it's going to be 0.584 times 0.416 times 0.584 times 0.416 times 0.584, which is equal to 0.416 squared times 0.584 cubed. Well, isn't that the same that we got the last time? It is. Since multiplication is commutative, no matter what order the shots are made, the probability will always be the same each time. So to find the exact probability of Kevin Durant making 2 three-point shots out of 5, we need to take into account the number of ways that he can make these shots. Well, how many different ways can he take 5 shots and make any 2 of them? We've already determined that the order in which he makes the shots doesn't matter. Therefore, the correct answer here is that it's a combination. The repetition is not allowed. In other words, you cannot take a shot back. And as I said, the order in which the shots are made does not matter. Recall that to find the number of different combinations of n objects taken r at a time, we use n factorial divided by n minus r, in parentheses, factorial times r factorial. So the number of ways that Kevin Durant can make 2 out of 5 shots is 5 factorial divided by 5 minus 2 factorial times 2 factorial. Or 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1. Well, the 3's, 2's, 1's cancel out, so we have 20 divided by 2, which is 10. So there are 10 ways in which Kevin Durant can make 2 out of 5 three-point shots during a game. And the probability for each of these ways is 416 thousandths squared times 584 thousandths cubed. Therefore, the probability that Kevin Durant made exactly 2 out of 5 three-point shots is the combination of 5 shots taken 2 at a time times 416 thousandths squared times 584 thousandths cubed. And when we put that in a calculator, we will get 345 thousandths or 34.5%. So let's try to generalize this formula using n, k, and p, where n is the number of attempts, k is the number of successful attempts, and p is the probability of each successful attempt. Well, we have 5 shots, and we're trying to complete 2 of them. So n is the number of attempts, k, 2 is the successful attempts, so that's the combination of n objects taking k at a time, times this 416 thousandths was the success rate, or the probability of each successful attempt. So that was p to the second, which matches the k value in the combination. So we have p to the k. And then we subtracted 416 thousandths from 1 to get the probability that it was unsuccessful. So 1 minus p is how we got this value, and it was raised to the n minus k, or 5 minus 2 in our case, which equaled 3. So that's how you end up getting the formula for determining the probability of exactly k successful attempts in n attempts in all. It's this formula right here. In math class, Mike is taking a multiple choice quiz. There are 10 questions. Each question has 4 possible answers. He didn't study for the quiz. What is the probability that Mike earns a 70% on the quiz if he guesses an answer to each question? Okay, well, in order to get a 70%, he's got to choose correctly 7 out of 10 questions correct. So this has to be our k value. And the 10 questions here, that's our n value. And we know that the success rate for each question, that's what we have to figure out. The success rate for each question, there are 4 possible answer choices and only one of them is right. So that's our p-value is 25%, or 25 hundredths. So we're doing a combination of 10 questions. We need to get any 7 of them correct. And we have to multiply that by the probability of getting it successfully correct, raised to the 7th power, because we need to get it correct 7 times, times the probability of getting it incorrect, which is 75% of the time, for the remaining 3. So if we put this into a calculator, we will end up getting, to do math, we're going to probability. We have to do NCR, so I actually think I have to put, okay, it gives it to me with blanks here. So we fill in the 10, and we're picking 7 of them. We're choosing 7 of them, and then we have 0.25 raised to the 7th times 0.75 raised to the 3rd. So our answer here so that's a 0.301% chance that he gets a 70% if he guesses on each question. And here's the solution laid out, and it verifies the answer that we found. It only shows the original decimal rounded off to the nearest thousandths place, which makes it 0.3%. When we originally calculated it, we went a little further out, but we still got the same exact answer here.